We've seen how matrix arithmetic and regular number arithmetic are similar, but there are also some very important differences. And the biggest one to remember is this. Matrix multiplication is not commutative. What that means is if you've got two matrices A and B, if you multiply A times B in that order, or if you multiply it in the opposite order, B times A, usually that's not going to be the same thing. So sometimes they can be equal, but usually not. So I want to do two examples here. Let's see. First up, example 201. We've got these two matrices multiplied here, and then we've got to multiply it in the opposite order. Now, if we do this, let's see, we're going to get a 2 by 2 out of it. And let's see, with this, I'm going to get 2 times 4 plus 3 times 1. So that's 8 plus 3 is 11. Then 0 minus 1. Then 4 plus 15. And then 0 minus 5. Okay, so we get that for this. Now, if we do these in the opposite order, again, we're going to get a 2 by 2. So let's see, we get, multiplying this across here, since there's just a 0 there, we're going to get 8, 4. And multiplying the bottom one across there, we get 6 minus 1. And then we get 3 minus 5. So notice we get two totally different matrices when we multiply these together. Now here's another example. On this one we've got 1, 2, 1, 1 multiplied with negative 2, 4, 2, negative 2. Let's use octave for this one just to make it easy and for instructive purposes. 1, 2, 1, 1. And then matrix B is negative 2, 4, 2, negative 2. All right, those look correct. So A times B gives us this. B times A gives us the same thing. So both of these give us 2, 0, 0, 2. So it can happen that you multiply two things together, you get the same answer, regardless of order. But most of the time, that's not going to happen. Another difference with matrix multiplication and regular multiplication is we don't have multiplicative cancellation. What that means is if we have AB equals AC, you can't just cancel that A off and get B equals C. So I want to demonstrate that here. In this case, what we've got, this is our matrix A, and this is C. This is B, and this is C. And we'll see that multiplying these things out, even though A and B are not the same, we're going to wind up getting the same answer here. So let's multiply these guys out and see. This is going to give me 2 minus 4 is negative 2. Negative 4 plus 8 is 4. 2 minus 3 is negative 1. And negative 4 plus 6 is 2. Right, over here, this will give me 1 minus 3 is negative 2. This will give me negative 2 plus 6 is 4. And then I get negative 1, 2 from multiplying the bottom out. So sure enough, we get that the products are the same. So in this case, we've got, this is AC, and this is BC. So AC in this case is equal to BC, but A is not equal to B. Now this is closely related to the next thing. In regular arithmetic, if we have an equation where we have xy equals 0, you can conclude that either x equals 0 or y equals 0. You use that all the time when you're solving an equation and you've got something like x plus 2 times x minus 3 equals 0. You split those and you say that one of them has to be equal to 0 to get a solution. But you can't do that with matrices. And here's an example. If we multiply these two things out, these are both non-zero. If I multiply them out, we're going to get an all-zero matrix. And one thing I mentioned up here is a matrix that consists of all zeros. A lot of the time we denote that with just with a bold 0 there. And the bold 0, it can represent any matrix full of zeros. If you just see it there, you just kind of assume that it's the correct size. Like in this case, if I had a bold 0 here is equal to this, it'd be assumed that's a 2 by 2 zero matrix. But let's multiply this out and show that it happens. So let's see here, we get 3 minus 3 is 0. Then 3 minus 3 again is 0. And then you get 6 minus 6 and 6 minus 6. So this is all zeros here. So we have, these are called zero divisors. One kind of interesting thing that you might notice, all of these matrices that we've dealt with in these two examples, well, not all of them, but in every one of the multiplications, at least one of the matrices has had what we'd call a determinant of 0, which means that one row or one column is a multiple of the other one. That's going on here. This row is a multiple of that one. This column is a multiple of that one. And the same thing's happening here. This row is just this one times -1. And so we're going to see later when we talk about determinants that matrices with determinant 0 are the ones that can do this sort of weird stuff where cancellation doesn't work, and you might get to non-zero matrices that multiply out to give you 0.